I'm sure Tim Ruffing, cryptographer at Blockstream, is going to do an excellent job explaining it. Please welcome Tim.
Hey. Hello, yeah, my name is Tim. I work at Blockstream. Oh, what was that? It's great. First second of the talk. Yeah, okay, it works. Again, so my name is Tim. I do research at Blockstream, and this is about robust asynchronous Schnorr threshold signatures. This is based on academic work, and it's joint work with my awesome co-authors, Vicky, Elliot. Elliot is also here. Please talk to him. Jonas and Dominic. Okay, so the context of this really is that we recently got support for Schnorr signatures in Bitcoin. So Bitcoin now supports Schnorr signatures. This has been introduced as part of the BIP 340, and this BIP 340, this Bitcoin improvement proposal, has been activated as part of the Taproot soft fork last November, okay? And there are three main reasons why we want to have Schnorr signatures, or why we prefer Schnorr signatures over ECDSA signatures that have been around in Bitcoin forever and can still be used. One of the things is that more is on the theory side that they have better provable security. So the theory guys can come up with better security proof, so this gives us more confidence in the security. Another thing is they're just more efficient a little bit. But the main thing, or at least the main thing for me, and the thing that this talk will be about, is that we can get easier constructions of advanced signing protocols. And the vision here is that we have on-chain support now for Schnorr signature verification. So if you're a Bitcoin node, you know how to verify a Schnorr signature. And this is the only thing you need to know about. This is the cool thing here. And then once we have this on-chain, we can build a lot of stuff off-chain on top of this. For example, we can build threshold signatures. This is something we will see in this talk. We can build multi-sigs. Maybe you heard of music or music 2. We could build blind signatures, whatever. As long as it looks like a Schnorr signature, we can put it on the chain and it will be compatible to Bitcoin. And the cool thing about this layer design really is that we have an on-chain consensus layer, and we had to change it once to introduce Schnorr signatures, but now it's kept simple. So if we want to do all of these off-chain things, we don't need to change the on-chain consensus layer again. And this is nice because changing consensus is really hard. Another advantage is that all these off-chain protocols are hidden from the verifiers of the chain, so from the nodes. At least if you just look at the blockchain, you just see a public key and you see a Schnorr signature, but you don't know if this Schnorr signature has been created just by a single signer or via an interactive process, maybe like via a threshold signature protocol running in the background or via a multi-signature protocol. The only thing you see on the chain is the single Schnorr signature, and you don't know how it has been created. And another reason is that, efficiency, I already mentioned this, but also compactness. It's just 32 bytes of data. So no matter what's going on in the background, what ends up in chain is really compact. And this is great because block space is so expensive. Okay, so what are threshold signatures? And maybe you have heard the term multi-sig. And I put this in parentheses here because multi-sig is more the term that's used in the Bitcoin engineering community and user community, and threshold signatures may be more the term that's used in the academic community. So the basic idea here is you have a T of n signatures. You have n signers that have shares of a key, and only if T of those come together and are willing to sign a message or transaction, they can do this. Just as a remark here, there are also n of n. There's this n of n special case where you need all the signers. This is what we call in academic literature usually multi-sig, and that's why I had on the previous slide I had threshold signatures and multi-signatures. But this is really about this case where we are flexible. We have T of n, and we want to have two basic properties here. One is called unforgeability, which is the main security property. I would say that actually means that the property is that T signers should be able to create a signature, but if you don't have T signers, they shouldn't be able to create a signature, right? You need those threshold T. So if you have T minus 1 malicious signers, even if they hold T minus 1 of the shares and they coordinate or they collaborate, they cannot produce a signature. This is one property we want to have, and the other property is called robustness. And this means that if you have T signers and they actually want to sign a message or transaction, they can really do this. And the way you can think of this is more like an anti-denial of service property. So Even if others want those T-honest signers, want to prevent them from producing a signature, they should still be able to produce a signature. And this is the main thing we will achieve in this talk, and I will define this in detail later. But for now, maybe this should suffice as a definition, right? Okay, so but actually, why do we want those threshold signature? And there are really a lot of applications. The most basic application is, say you have a 2 of 3 at home, you have some coins, you want to raise your security of your wallet, so you could, instead of using just one device or one wallet, you could split the key into 3 pieces, give the 3 pieces to different wallets and store them in different places. And this is great for security, because now if an attacker comes and steals one of your shares of the key, they can't spend your coins, so they can't steal the coins. But also if you accidentally lose one of those devices, it's not bad, because you still have 2 of those left, right? So it increases security, but also at the same time it increases reliability. And of course, you can do maybe 2 of 3 at home, but if you have a lot of coins, like Bitfinex, for example, I've heard they do a 3 of 6, so they increase the numbers here to get even higher security level. And another thing where this is useful is, for example, Blockstream. One of our main products is Liquid. Liquid is a sidechain. That means you can send Bitcoin into Liquid, and also you can then ask the Liquid sidechain to give you those coins back on the Bitcoin mainnet again. And while those Bitcoins are stored in the Liquid chain, they are maintained by what we call watchmen. Watchmen are nodes that run a wallet, and they keep those Bitcoins safe. And of course, also here we want to have a higher security level. So currently we have 11 or 15 here, but actually we would like to go higher. And there are a lot of applications really for this. So what you can currently do, or what you always could do in a sense in Bitcoin, is using what I should call here maybe naive multisig or naive threshold signatures. Currently, after the Taproot update, this can be done using object-sig-add. This is a special opcode in the script. And what it really means is you literally give all n public keys. So we have n signers, they all have a separate public key, and then in the script you say, okay, these are n public keys, and the script says, okay, if you want to spend this, give me T signatures under those n public keys, of course, under different public keys. And so a valid threshold signature would here just be T signatures. But this is, first of all, I should say that this is very simple. That's why it can be good. Another advantage of this possibility is that the key generation is non-interactive. So every signer can just generate their own key pair, and they don't need to talk to each other while key generation. Also, the signing process is non-interactive. Again, this just means that if I'm one of those T signers, I can just create a signature locally, or at least this one part of the signature locally, and can send it to the others. And another interesting property that we have is that's accountable. So that means you could tell who are the T signers that actually spend the coins. It could be interesting. I mean, if you really got T malicious parties and they steal your coins, then at least you can tell who stole them. Not sure how useful that is, but in certain scenarios it might be useful. But the big drawback here is that you really need to put those n public keys on the chain, and then if you spend the output, you need to put the T signatures on the chain. So it's basically the opposite from what I told you earlier. It's not at all compact. And this also means that the parameters T and N here are very limited, because block space is so limited. So there is no real fixed limit, but you couldn't really scale this up to 100 or so. It's just not feasible. And another big drawback is because all those you see those n public keys and the T signatures on chain, so everybody can tell at least that this is that there is a T of n multisig going on. They may not see who is involved in that and so on, but they can at least tell that this is a T of n multisig, and they see the numbers T and n. So they can see that this is not an ordinary transaction created by ordinary wallet, and that's of course is not great for privacy. So actually what we want is native threshold signatures. So the idea here is that threshold signatures should really look like ordinary Schnorr signatures, and this is what this talk is about. And recently there has been a very nice paper called Frost, maybe you heard of that, Flexible Round Optimized Schnorr Threshold Signatures, by Ian Cole, Chelsea Comlo and Ian Goldberg, of course, that way around. And this is great scheme. They have proven it secure under concurrent signing sessions. What this means is that you can run, so if you are one signer, you can run multiple signing procedures in parallel, and even then, it's still unforgeable. You need a suitable key generation protocol, okay, but this is a detail I won't go into here. The problem here is really that this Frost protocol, it's very simple, but it doesn't provide robustness. So this doesn't provide this anti-DOS property that I mentioned earlier. And this is what I want to fix in this talk. So, but first of all, let me walk you through the basic setup of how Frost would look like from a structural point of view. So in this example, we have 4 signers, so n equals 4. And in Frost, we assume we have some central coordinator. And central, first of all, sounds a little bit bad, but I can tell you why it's not that bad. What happens here is that the signers, they only talk to each other via this coordinator. So they don't have direct peer-to-peer connections to each other, they just talk to the coordinator. And the reason why that is not so bad actually is that this coordinator is not trusted at all for unforgeability. So even if this coordinator is totally malicious and also colludes with the other malicious signers here, they couldn't be able to steal your coins. But it's relied upon for robustness. And what I mean by this is, this coordinator is a little bit like the network. So we have those 4 signers, they want to create a signature. Let's say we have a 2 of 4, so they need two signers to do this. But somehow these 2 signers need to talk to each other, right? If they can't talk to each other, they cannot possibly run a cryptographic protocol. And the way they talk to each other is just via the coordinator. So it's, if we say we assume that there's a coordinator, it's a little bit like saying we assume that there's a working network. If we don't have a working network, well, we can't talk to each other, we can't make any progress. Yeah. And in this setting here with the signers and the coordinator, the goal that I want to achieve now is this robustness property. And what does this actually mean in detail? So consider a run of the signing protocol with all n signers. So yeah, we have those 4 signers, and they agree on a message they want to sign. And T of them, so we have enough signers that are actually honest and willing to sign a message. But now the remaining n minus T signers, they are malicious and they want to prevent the honest signers from obtaining a signature. And even if this is the case, we would like this robustness property, which means that even if we have the n minus T malicious signers, it's guaranteed that the signing protocol will terminate and output a valid signature. So we can make progress, we can sign even though the others are malicious. And just technical detail here is that we are satisfied if the coordinator outputs a valid signature. But it's really just a simplification, because if the coordinator has the signature, it can always send it around to the honest parties or to the blockchain directly. Yeah, so this is really just a technical simplification. And the network setting, or the network assumption in which we want to assume this robustness property is an asynchronous network. What that does mean. So the idea here is that we only assume a very weak thing about the network. The only thing we assume about the network is that messages between honest signers and the coordinator arrive eventually. When I say eventually, it means they arrive, but I can't really tell when they arrive. There's no fixed deadline. So we don't assume any deadline in which messages actually do arrive. And this is really if you're honest, what we need in the internet, because the internet doesn't make any guarantees, right? It actually doesn't guarantee delivery at all, but if we don't have any delivery, we can't make progress. So this is basically the minimum we can assume from the network. And what this means in practice is that, let's say we have a signer, and the signer is supposed to send a message to this coordinator on the right, and the coordinator may not receive the message, so maybe the message is just slow and it will arrive a minute later. Or maybe the signer actually has crashed or is malicious and will never send a message. But the point here is that at no point in time the coordinator can conclude that this signer is malicious or crashed or offline, because the message could always arrive later. So this in practice, yeah, so the coordinator actually doesn't know. In practice, this means that we cannot have timeouts in our protocol. If you would have a timeout and conclude at some point that the coordinator would at some point conclude that the signer is offline and will never respond, then actually what could happen is that the signer will respond a second later. So this is a very strong setting, or a very weak assumption, so we need to build a strong protocol to make that work. Okay, and the contribution of our academic work is Roast. And in one sentence, Roast is a wrapper around Frost that turns Frost into a robust threshold signing protocol. So I told you Frost doesn't have this robustness property, and now Roast is a way to use Frost in a robust way. So maybe also one comment here. A lot of people have asked, okay, what is the relationship between Frost and Roast? What should I use? It really depends on the setting. It's not like they are competitors. It's really like Roast builds upon Frost and makes it better. But if you really need Roast, depends on your setting. But we'll see that. Okay, so how does it work? Setting the stage. Again, we have four. We have an example with 4 signers. N equals 4. We have the coordinator in the middle. And just some basic conventions here for the rest of the talk. So we always have a 2 of 4 example, just because it fits so nicely on the slides. When I say we, I always speak from the point of view of the coordinator, just because it's easier for me to speak about it, because I don't have to always say the coordinator does, but you can just say we do stuff. And all messages we receive, so now the coordinator, right? So we are the coordinator. All messages we receive are valid. This sounds like a strong assumption, but actually it's not, because in Frost, really what happens is that whenever we receive a message, we can immediately tell whether it's valid or not. So we could in theory, if we get an invalid message, we can just ignore it and pretend we never got it. Of course, in practice, you wouldn't do that. You may want to disconnect the connection, assign some penalty to the node or whatever. But in theory, for the purpose of this talk, it's just okay. We just assume that we ignore invalid messages, and the consequence of this is that all messages that we actually arrive are valid. Okay, and when I say session, it always means Frost session. Okay. So how does Frost actually look like? So Frost has 2 rounds. Or let's say rounds of communication. In the first round of communication, all the signers send what we call nonces. I don't need to tell you what a nonce is. It's just the name I use for this message in the first round. So let's say, for example, the signer 1 here sends. So let's call them 1, 2, 3, 4, just to make it easier to talk about them. So signer 1 sends a nonce. What the coordinator does is it waits for T nonces. So maybe this guy now, signer 3 sends a nonce. Now we have 2 nonces. I said we have a 2 of 4 example, so T equals 2, so now we have 2 nonces. What we can do now as a coordinator is we start a new session. We start a new Frost session with those 2 signers. So that's why I marked them blue here. So the crucial thing that's happened here is now that as a coordinator, now I commit that I will finish the protocol with these 2 parties. This will be crucial. What the coordinator now does, it got those T nonces, it aggregates them into, what we call aggregate nonce and ag nonce, okay? It sends this ag nonce back to the 2 signers. Again, I don't need to tell you what an ag nonce is, but it's just the structure of the protocol. And now those 2 or T signers in the session, they are supposed to send their signature shares back. This is the second round. And maybe this signer 1 sends a signature share back. And what may now happen is, because it was slow, now signer 4 finally sends their nonce. But at this point, we can't really do anything with it, because we are already committed to using the 2 signers on the left. So we would just ignore that message, because it's not really useful for that run anymore. Now signer 3 may send a signature share, and now we are in a good situation, because now the coordinator in the middle has received 2 signature shares. That's enough to complete the protocol. We need 2 of 4, right? So in this case, everything worked out. The coordinator outputs a signature. This is a successful run of Frost. Or let me say session. Okay, but the problem here is that Frost is not robust. So what could happen is that after we received maybe the signature share from the first signer, it might happen that the signer 3 just will never respond. And again, we can't tell whether it's crashed, whether it's malicious, whether it will respond later. But at that point, we could stall forever. And it doesn't. So yeah, and it doesn't help at all that this signer may later send a nonce, right? Because at some point we had to commit to those 2 signers on the left. So in that sense, here we are stuck. If the signer 3 never responds, this session will take forever and we can't make progress. Okay, so one easy way to fix that, easy in a sense, is we get some trivial solution. We just run a frost session for every subset of size t. This works. We can do this even in parallel, but it's in this case it's 6 sessions, so it's still handleable. But in general, this needs n over t sessions, and this is pretty quickly infeasible. I mean, in this case, yeah, as I said, we have 6 sessions. In this 15 or 11 or 15 example, that's yeah, you may be able to you may be able to do this in practice. It's not elegant. Well, yeah, if you have if you have something like 76 or 67 of 100, well, yeah, no chance, right? So that's not a good idea in general. What could we do instead? So again, let's go back to this situation where we got stuck, right? So here, this is the point where we received a partial signature from the first signer, but not from the third signer. And we don't know how to continue here. Let's just make some basic observation about this situation. First of all, we have a session running, and there's no reason to abort this session, right? Because we don't know if the signer will come back or not. It might come back in the future, so just let the session open. There's no reason to abort something. We just let it run. The second thing is this pending signer, signer 3. If we start a further session, we shouldn't really include him, right? Because he seems to be slow. It's no point in getting the signer in the session. The second or the third thing here is we actually need to start a further session to ensure progress, because again, we don't know if this guy will respond. So this session is not guaranteed to make progress. So the only thing actually we can do is start another session. And another observation is that now we saw that maybe signer 4 comes back with their first round message, the nonce, and here it would have been nice if when signer 1 sent their signature share, the blue arrow in a sense, they would have already sent a further nonce for a future session, just in case we may need it. Because if we would have done this, then at this point, when the fourth signer sent their nonce, we could immediately start a new session, because now we have again two nonces from 2 different signers. And this is just this is just this observation. So if we have big effect, a fresh nonce on every signature share, we could start a new session immediately in that situation here. And now we just translate those observations into rules, and this will guide us. This will guide our design of Roast. So the first idea is always keep sessions open. The second idea is we maintain a set of pending signers, where pending really means not responding. And this is just to make sure that we don't include those pending signers when we start fresh sessions or new sessions. The third point is whenever we have 3 signers that are not pending, we start a session with them. And the fourth thing is, piggyback a fresh nonce on every signature share. It's just the trick I showed you earlier. Okay, let me walk you through this example execution. So again, our 4 signers. In the beginning, they are all pending. I used this clock symbol to indicate pending. Because in the beginning, they're all supposed to send their first message, the nonce, and they haven't done this, so we mark them as pending. So maybe now the first signer sends them a nonce. Now the first signer isn't pending anymore. Very easy. Third signer sends a nonce. It's not pending anymore. Now the coordinator, or we assign those 2 nodes again into a session. Now I add a number here just to indicate that this is the first session we start. Now we send the egg nonce back. They are pending again because now they are supposed to respond. Now maybe this signer again responds with a signature share. It's not pending anymore. And actually, because this guy is not pending anymore in the first session, we can say it's not a session anymore. It has completed the first session. That's why I mark it red again, white again. Now maybe the fourth signer responds with a nonce. It's also not pending anymore. And now we again have two signers that are not pending, so we put them in a new session, call it session 2. And now, because now they're supposed to respond again, they're not pending anymore. Sorry, they're pending again. Yeah, everybody's pending now. And now maybe this guy is very late, second signer now sends a nonce, not pending anymore. Now this guy comes, sends a partial signature, done with session 2, not pending anymore. And now again we have two signers that are not pending, so we start a third session with them. Okay, and here in this at this point I claim that this is a situation where the next message will finish the execution, because we know that there are two honest signers that are willing to sign and that their messages will eventually arrive. So no matter who these two are, we will always make progress now. So for example, if these two respond, session 3 will finish. If this guy responds, then session 2 will finish, and if this signer responds, then session 1 will finish. So no matter who will respond here, we will always make progress. And we know that there are at least two who will respond because two are honest. So in this situation, we are in a position where we always finish the protocol. And the key invariant that made this work is that every signer is pending at most one session. And this really comes from the fact that whenever we had a pending signer, we made sure not to include it in further sessions. Right? So that means every signer can hold up at most one session. Because if it holds up one session, we will never include it in a further session. Okay, and now actually we can, in the paper, we have a formal proof for this robustness property. Informal way of defining what robustness is here is that we say the coordinator outputs a valid signature after initiating at most n minus t plus 1 signing sessions of Frost. And the idea to prove that is from the key invariant I mentioned on the earlier slide. We know that every signer can hold up at most one session. That's what I just explained to you. So that means that the n minus t malicious signers, or we call them also sometimes disruptive signers, they can hold up at most n minus t sessions. But because we start n minus t plus 1 sessions, one of them must go through. And the other thing that we need to formally argue in the proof, if we do this correctly, is that we actually always are able to start a new session. But this is also guaranteed because we know that honest signers will respond eventually, because the network is asynchronous, that's what we assumed. So we can always, eventually we can always start a new session, because eventually we'll have T signers that are not pending. And so because we can always start a new session, we can always make progress. This is really all of the basic ideas. Of course, if you look at the paper, the proof goes a little bit more into detail, but this is really the high-level things that make the idea work, yeah. Okay, and we also implemented this, at least as a prototype. Really, I have to say, very unoptimized in Python. The elliptic curve operations are done by with the fast ECDSA library. That's really a Python library. Don't be confused by the fact that it says ECDSA. It exports elliptic curve operations, so we can actually implement Schnorr signatures with it. It sounds a little bit strange, but it works. And under the hood, it uses GMP, which is a general purpose C library. So part of it is in C, part of it is in Python, but even GMP is really not optimized. So this is actually slow code. And as a network setup, we use the server in Francisco to run the coordinator. We use the server in Frankfurt to run a lot of signers. Now it may sound strange that all of the signers are on a single server. It's not perfectly replicating things like the internet, but it's not that bad, because anyway the signers only talk to the coordinator, right? So they don't talk to each other. So we always have this. Every message goes over the Atlantic once, at least. So this gives us a round trip time of 150 milliseconds. And in this setting, we simulated an attacker basically by saying that these n minus N- the most strong or the strongest attacker you can imagine. But it's an attacker really like it simulates random failures on the internet. Maybe signers crash. This is what happens, right? Nodes crash randomly. Network connections may be down, and so on. This is what's simulated here. And in this setting, if the signers that crash don't coordinate, so they can't talk to the other crashing signers in a sense to crash in a clever way, then if we have a 11 or 15 setup, then this protocol, even our unoptimized prototype, terminates in below a second. And the same even for this huge setup with 67 out of 100 nodes. It still terminates in 0.7 seconds. And of course, this is not a very clever attack if the nodes crash randomly. We also simulated a setting where the crashing signers, they first talk to each other. In a sense, they're actively malicious to make sure that they disrupt as many sessions as possible, and then the numbers go up. But I still claim that for this stronger attack scenario, that's still realistic. In this 11 or 15 setting, we terminate in a second. And even if you have 100 signers, we terminate in 7 seconds. And this is really a strong attack. That really means that like here, 33 signers are actively malicious trying to prevent you from getting a signature. I think if you're in that setting with your federation or whatever you run, you might consider anyway, transitioning to a new federation or something like this. But even then, we terminate in 7 seconds. And one final word, I said a lot about the trust in this, or not trust in this coordinator. It's actually only a network assumption. But if you really don't like the idea that there is a trusted coordinator because it's center point, it may crash, and if it's crashed, then the entire protocol is down and so on, you can actually get rid of this. And again, the idea is pretty simple. You pay a little bit more in communication. The idea is, again, we know that there are at most n-t malicious signers. So if we run n-t plus 1 again, runs of roast now, replicated runs of roast, and use n-t plus 1 signers as the coordinators, then we know that one of those coordinators, again, will be honest, because we have at most n-t malicious signers. So if we take n-t plus 1 signers, one of them will be honest. And this guy will play an honest coordinator, and then we know that run will work, because there we have honest coordinator. Of course, this increases communication by a factor of n-t plus 1, but it really gets you rid of the coordinator. And you can run it in parallel. Okay, so to sum up, Roast is a wrapper. Roast turns Frost into a threshold signing protocol that first of all is robust, so it has this anti-DOS property, even in asynchronous networks. And it's very simple. All it does is really it starts multiple Frost sessions. And the cool thing about this is that it's also not that hard to implement, in a sense that you don't need to be a cryptographic engineer, for example, to implement this. If you have an implementation of Frost, all you need to do is call Frost in a clever way. But you don't need to go in all the crypto details and make sure you get them right. It's just really a wrapper around Frost, and you start Frost sessions. Okay, and if you want to learn more, or first of all, if you want to have those slides, you can find them here. If you want to get into all the details, please read our paper or talk to me. We also have a blog post, and you can also look at our prototype and our benchmarking data on GitHub. Yeah, thanks. And yeah, of course, feel free to ask questions. Yeah.
Hey, I'll start it off, I guess, and then I'll hand it off to whoever wants it. My question, and this might be because I don't know what the hell's going on, but after the nonce session, it seems like you're able to terminate the session very quickly, which I don't really understand. Like you're saying in one case it'd be like less than a second, and then the 67 out of 100 it was like 7 seconds. The thing that I don't get is if you have a attacker, or I don't really even know maybe what an attacker is in this situation. I'm just thinking of someone after the nonce round, they just go quiet and they just stay pending, which I was thinking is that not covered here? Because I was thinking that would be like a very long, like multiple minutes or something pending, kind of thing.
Okay, yeah, there are multiple things I think here. First of all, when I say attacker, I really mean this is more like from this security thinking that there is one single attacker that controls all the malicious guys. So when I say attacker, I just mean the set of all malicious signers here. And you're exactly right. What we simulate is that they go silent after the nonce round. So they send their nonces, and then I say they crash, but it just means they don't respond anymore. So this is exactly the scenario that we're looking at. And now the reason why this is still so fast is because our protocols exactly work in this asynchronous scenario. So I explained earlier with this on this slide where I have the asynchronous network that we are not allowed to have a timeout in our protocol. So we never need to wait for messages from malicious parties. We can always make progress when honest parties send messages. That's why we don't have this long timeout for a minute or so. This is really what makes this fast. So even if those guys don't respond, the honest people will respond, and this will give us progress.
Okay, so this is a timeout for a good node, not for like a stale session or whatever, because they're already going to be done with that session. Is that kind of like the idea?
No, this is really the running time. In this case, the malicious parties don't respond, but we still, because the honest parties respond, we still finish in this time.
It's the maximum time to get a signature given coordinated attack.
Okay.
And
No more than 7 seconds will need to wait to get a signature.
It just shows you how confused I am. Because he just said there's no like timeout in the protocol. So now I'm thinking like, where's this?
Yeah, maybe we can chat about this later. Then I hope we can get clearer.
All right, I will. Who else has a question? Oh, I'll start here.
Yeah, just as a quick understanding. When you send these nonces as a piggyback, would it be possible to kind of jumpstart that process by just generating and sending more nonces in the first step, basically, by just sending 100 nonces from the get-go, and then you can avoid some rounds of communication? Or
I don't think you can avoid rounds, but there are a lot of these optimizations are possible, really just because the protocol is essentially simple and starts only on the frost sessions. You can really play around with this. You could also say, for example, as a coordinator, you wait a little bit. When you wait for messages to arrive, you wait a little bit longer. You don't immediately start a new session. Maybe this saves you some communication, but you pay a longer delay, and so on. You can really tweak around with the parameters a little bit to optimize it a little bit, maybe for more communication, but higher delay, or the other way around. Yeah, this is all possible.
Okay, thanks.
So the robustness part essentially begins, I guess, in a 204 example, when the third person, not in the initial quorum, sends a nonce to the coordinator. Is that right?
Yeah, this is where. So this is where we go from frost to roast in a sense. Before that, it was just a frost example, and this is where then roast starts. If this is your question.
Okay, and then I guess my question is, what if the second person is just taking a really long time, and say
You probably are here somewhere, right?
Yeah, like at the first round, say the second person is just taking a super long time.
You mean the designer in the bottom left? Yeah.
Yeah, the one at the bottom left takes a really long time, and like say, let's assume the person at the bottom right is a malicious actor and decides to be disruptive and just triggers the robust process, which ends up requiring more signing sessions. That could happen too, right?
That could happen. Yeah, it's not a problem. It's just that we send a little bit more of messages, right? So in that situation here, either this guy responds at some point, and then as soon as he responds, we immediately finish.
Okay.
Of course, it might happen that because he doesn't respond, we go on and start further sessions. But That's not really an issue. We spent a little bit of communication, but it could still happen that this guy comes back at some point, and then we're done. Cool.
Gotcha. Cool. Thank you.
Yeah, in your presentation, you were kind of agnostic of the actual implementation of Frost, but I would be interested in, did you look into if you actually have to generate new nonces for each of these rounds, or could you actually reuse them? It probably depends on how you aggregate them.
I can't reuse them.
Okay.
No way. Don't do that. Yeah.
So what if you used what if you're doing this over a protocol that had more than 2 rounds? Like it seems like it generalizes to any 2-round protocol, right? In the asynchronous network model.
Interestingly, it doesn't. We thought about this, and this idea doesn't really generalize to more than 2-round protocols. And I think this is why. And I guess it's hard to explain now why this is. We can take this offline, I guess. But this may be the reason why no one has discovered this before. Because I claim it's very simple. I'm sure there is some 30-year-old computer science paper about a totally different thing, different field that contains the exact algorithm, but you haven't discovered it yet. And I think this idea is pretty simple, and no one got this earlier because we didn't have a protocol where we can this apply to. Now we have Frost, so suddenly we have a protocol where this can be used. So it makes sense to think about these things. But it really doesn't work for a protocol with more rounds. It wouldn't work.
So I was interested in knowing more about the coordinated attack. Like, why is it taking 7 seconds in coordinated?
Yeah. So the difference between the let me go to that slide. Actually, the coordinated attack and the coordinated attack and the uncoordinated attack is that in uncoordinated, so that the malicious signers or the crashing signers, they don't talk to each other, right? So it could happen that we start in the beginning. Let's say we have this 67 of 100 setting. We start a session with 67 nodes. And now it could happen that 30 of them crash. That means that the attacker now has wasted 30 nodes to stop a single session. And they will all be excluded from further sessions. So in a sense, the coordinator was lucky and could exclude 30 malicious parties at once. Whereas in the coordinated attack, those 67 really, they talk to each other. All the malicious parties within those 67 talk to each other and make sure that there's exactly one that doesn't respond. So the coordinator can only exclude one malicious party. And this means we really need, in the worst case, we need 34 rounds or 34 sessions of Frost. And this is why it really takes long then. Whereas in the other setting, we are probably lucky. We exclude a lot of malicious parties in the first session. We exclude some in the second session, and at some point, no more malicious parties are left over. Yeah, go ahead. Oh yeah.
Yeah, but like we are not waiting for them to not respond or basically not crash, right? Like everything is happening concurrently, I assume. So
right. I mean, we are not excluding them in the sense that we kick them off, but when we start a new session, we will make sure they are not in this new session. So we immediately start a session where we don't include all the 30 malicious nodes that try to stop the first session.
I think maybe the confusion, and same with Mike's initial question, right, is that we actually don't start a new session until you send the nonce for the next session along with your signature from the last one. So there's a full round trip before every new session can be started. I think that might be where the confusion is. I don't know.
Maybe, yeah.
I was also trying to get more detail on the attack. Is the attack for like the coordinated attack to try to get each one of these guys to come in sequentially to slow down the process a little bit more?
Yes, exactly.
Okay, and if
so
they came simultaneously, you could cancel them out.
Right, yeah. So in the coordinated attack, you have really the attackers try to have select one single attacker or one single signer that stops the first round. Then we need to start, or the first session. Then we need to start the second session. Then there is a unique malicious signer that starts that tries to stop the second session and so on. Yeah.
Any more questions? Do you want a mic real quick?
Yep.
Good.
Yep.
Okay. Okay, thank you so much.
Okay. Thanks.